Alrighty. So, yeah, we'll just kind of, well, let's not jump right in. Let's maybe kind of refresh our memory a little bit of what we've been talking about, right? So this whole unit kicked off, because this is also helpful in preparation for tomorrow's quiz and stuff like that, right? Kind of get those big pictures and things. So this whole unit, okay, is kind of predicated on the idea of using polynomials, okay, to approximate functions that are not polynomials, right? And so we started out with this function e to the x, okay, and the way we kind of built a polynomial to try and match then this function e to the x is we start with the idea of, okay, we're going to kind of do this in steps, right? And we'll do just like the first step, we'll just say, okay, let's just make sure our polynomial is the exact same as e to the x at the point x equals 0, right? And so we came up with this very simple, degree 0 polynomial where it was equal to 1, right? This polynomial 1 is approximately e to the x near the x value of 0. In fact, it's exactly e to the x at 0, but near 0, it's not a bad approximation either. Okay, but it's like, well, how can we improve this? And so we increase the degree of our polynomial by 1, making sure that not only the original polynomial is equal to the function at x equals 0, but also ensuring that the first derivative of our polynomial approximation was equal to the first derivative of the actual function. Okay? And then as we proceeded there, we continued to do more and more derivatives of our approximating function, right? So then we did like the second degree polynomial, making sure that the original function, the first derivative of our function, and the second derivative of our function all matched up to the original first and second derivative of the approximation, I guess, making sure those matched up. And it gave us something like this. And then as we proceeded here and expanded further and further, we started to see, hey, wait a minute, there's a pattern here, and it's a sum. Okay, and so this then created that Maclaurin series at first, right, because we were centered at 0 specifically there. And we had this pattern for the Maclaurin series, okay? And so we wrote out a few more terms, stuff like that, and then we started just doing it, repeatedly, just trying different things. So this was for cosine of 2x, right, and then using it to approximate. Then we were like, oh yeah, we can generalize this and say it doesn't have to be centered at 0, it can be centered anywhere, and so that just, results in x minus c and f prime of c there. So instead of evaluating the function at 0, you evaluate at wherever your center is, and you just do a horizontal shift, with your x coordinates there, okay, for the center, right? Because if you put your x coordinate and then minus the c, that's a horizontal shift, right, left or right, depending on whether c is positive or negative there. Stuff we've seen in the past, okay? And then we went through that and looked at some more Taylor series, some examples there. I don't think I've got anything too crazy. Yep, just kind of writing out those Taylor polynomials and stuff like that. Okay, and then we got into power series where we started to come up. Okay, so we were at this point we'd only been doing finite approximations, a finite number of approximations, and so it's like, well, what if we carry this to infinity, right? What are we going to be seeing? And so we will see that exactly if we carry it out to infinity, we will get the exact function representation in a series format. So for example, right, we got that e to the x is precisely the series, the sum from 0 to infinity of x to the n over n factorial, right? Just using the pattern. What's that?
So I forgot which class it was.
You figured it out though? Okay, very good. Yeah. ln(x), we did that one too. That's not one we have to memorize, but we were able to do it, so there it is, kind of thing. Okay, we then did it for sine, we did it for cosine. Again, the Maclaurin series centered at 0 there. And then finally, we came up with this kind of like table to help us remember the 4 Maclaurin series that we need to remember, right? Which I told you earlier when we were talking about the homework, right? So e to the x, it's all the factorials, not alternating. Sine of x, it's only odd powers and factorials and alternating. Cosine is even powers and even factorials alternating. And again, you can distinguish sine and cosine. Sine is an odd function, right? It's rotation. It's got symmetry, rotational symmetry about the origin. Cosine is an even function, right? It's got symmetry over the y-axis. Okay. Sine at 0 is 0, and so that's why we start with. You can kind of think the first term is the 0th term here. Cosine at 0 is 1, and so the first term there starts at 1. So that can also help you kind of kick things off as well. Okay, to see that. And then of course we have our geometric series right here as well. 1 over 1 minus x is kind of like that geometric series there. Okay. So those 4, and of course transformations of those things we should be comfortable with. And so we did transformations then of those things, right? If sine of x, for example, is this, then what would sine of x squared be? And we got that, You can see it gets very complicated if we try and do it, kind of like the normal way with coming up with the actual derivatives and things. Did the same thing here with e to the x, transform that to make it look like that. Okay, and so on and so forth for several others here. Okay, identifying their transformations and things. And let's see. Oh, we also did some fun things like taking the derivative. Okay, the Maclaurin series for the derivative of a function, right? Or finding the Maclaurin series, or finding the series for the integral of, we're integrated like a Maclaurin series basically, and stuff like that, or the first couple terms at least. Okay, and then remember we can also use, right? We can also use these ideas to find the 19th derivative. So for example, we had kind of two different strategies here of this. Option one, right, was to just kind of like see the pattern here, right, write out the pattern, which isn't too terrible because this one repeats, but for some other ones they might not repeat, so instead your other option is to use our typical format there for, a power series where it's the nth, if we want to find the nth term of that series, it's going to be the nth derivative at 0 times x to the n over n factorial, okay, and especially since we're doing it at 0, right, we can plug the 0 in there, and then we see that that's going to match to this term right here again because we already established our general term right there. And so we're seeing, okay, well the 19th derivative of f at 0 has got to be this piece right here, right? Because the x to the 19, that corresponds to the x to the 2n plus 1. The 19th factorial corresponds to the 2n plus 1 factorial for the 19th term. So those are taken care of there. And so then the 19th derivative at 0 is just going to be this alternating 2, positive or negative. Negative in this case because it's, negative 1 to the 19 there times 2. All right, and that allows us to figure out what that nth term is going to be. Okay? Or at least, the 19th derivative is going to be, not the 19th term. We can figure that out too, I guess, but yeah. All right, so, that was a lot. All right, questions on anything there? We're all good, all caught up, right? All right, so today then we're going to be looking at power series still, right? So in the last section, we dealt with Maclaurin and Taylor polynomials that when added up, resulted in Maclaurin and Taylor series. In this section, we will focus on any power series and its features. Okay, so not necessarily Maclaurin or Taylor, right? Not necessarily sine or cosine, things we're familiar with, just kind of any power series. So going back to the definition of a power series here, if x is a variable, then an infinite series of the form sum from 0 to infinity of a sub n, x minus c to the nth is equal to, and again you can see right there, okay, something very typical there, a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, so on and so forth. And that's called a power series centered at c. Okay? You'll notice here that it's different than, it's like, this is, so the power series is a more general kind of like, more general category, right? Within power series, we have the Taylor, right? The Taylor, which specifically has, the certain, quantities of the derivative there. And in the Taylor series, we have the Maclaurin series, which is specifically a Taylor series centered at 0. Okay, so biggest category power series. Then within that is Taylor series, which has a specific, sequence a sub n there that goes in front of that x minus c to the n factorial, or sorry, to the n. And then the Maclaurin within the Taylor series, a specific kind of Taylor series centered specifically to 0. Okay, so all that stuff there. When representing a function f of x as a power series, okay, the domain of the function. In fact, maybe I'll write that out here real quick. So just to like recall here, right, a Taylor series is in the form n equals 0 to infinity. Okay. Oops, of c. Okay. So it's for a Taylor series, right? It's a specific kind of power series where it's the nth derivative of f at c over n factorial. That is a c right there. It's supposed to be a c over n factorial then times the x minus c to the n. Okay. So the Taylor series is a specific kind of power series. This a to the n here. Not a to the n. A sub n is this right there. That's the a sub n piece right there.
What's in parentheses?
C. It's supposed to be a c. Those are c's. So you can see how that Taylor series is also a power series, right? Power series is a more generic, kind of category, I guess, more general category. That a sub n can be more generalized instead of just specifically what the Taylor series is. Okay. So when we go back here, right, when representing a function f of x as a power series, right? So some of our functions that we came up with, for example, like e to the x, we know that's represented by a certain power series. Sine of x, cosine of x are represented by a certain power series, okay? That function's domain, the domain of the function f of x, is all the values of x for which the power series converges. So let's take a look at a function with a power series function that we should be familiar with, right? 1 over 1 minus x. Okay, that is a function, okay? And we can talk about the domain of the function here. Well, let's first of all talk about, that's the series, if you recall, right, from n equals 0 to infinity of x to the n. But the domain of this function, okay, it says here, is all the values of x for which the power series converges. All right, we had the stipulation here that this series only converges for what values of x? Do you remember? There wasn't any x, you could just say it converges. Okay, yeah, and there's the absolute value, right, of this x must be less than 1. Okay. Absolutely. Or in other words, or you could say -1 less than x less than 1, like that. Okay. And so this series only converges to 1 over 1 minus x if x is less than 1. Okay. Or -1 less than x less than 1. Okay. So the geometric alternating series and ratio tests are very helpful in these situations. Okay, but other tests can also be just as useful. The set of all x values for which the power series converges is known as the interval of convergence here. So in this very particular case, right, of the geometric series, if we get, something like this, we know that this is the interval of convergence, right? -1 to 1. -1 to 1. Okay? So that's the idea there. Now, there is something that's kind of interesting here that -1 to 1, if you imagine plugging these back in here, right, at the endpoints themselves. So certainly between -1 and 1, we agree that this thing converges, right? But at the endpoints themselves, we can kind of convince ourselves and see, well, if I plug in a 1 here, what's this going to result in? Undefined goes to infinity, all right? But if I plug a -1 in here, what's going to happen? It'll become 1/2. That's finite value. So what we're going to find here is that sometimes the endpoints will converge. Sometimes the endpoints will also diverge. We're going to look at that too. So not only are we going to have to determine the interval of convergence, but we're also going to need to look at the endpoints to kind of determine here whether they also converge or diverge at the specific endpoint and stuff like that too. Okay? Because keep in mind here, if you imagine plugging the 1 in here, a positive 1 in here, you'd be adding 1 up an infinite number of times. But if we plugged a -1 in here, what would it now become? It will be -1 to the n. That's now an alternating series, and that would converge by the alternating series test, right? So this thing would converge by the alternating series, but it would diverge if it was a positive 1 kind of thing. Okay, so we get those, kind of dual aspects there. So in this case, we're going to also have to look at the endpoints, not just the interval itself. Okay, but let's continue back to where we started from. So we're just talking about the interval right now. So for a power series centered at C, one of the following cases is true, along with and we'll give like a graphical representation, okay? So option 1 for your interval of convergence for a power series, the series converges for all x, okay? The series will converge for all x, okay? In other words, R, which we'll call the ratio of convergence there, okay? Or sorry, not ratio, radius of convergence, it'll be equal to infinity. So in other words, if you think about a number line here, okay? And we have our polynomial approximation centered at C. C could be 0, C could be some other number. All right. As we continue to add to our power series here, it's going to continue to grow and grow. Well, I guess this is more in the Taylor series case, but it'll grow and grow and get closer and closer to our function. Okay. And so the idea of this then, again, if the series converges for all x, that means our interval of convergence, okay, is going to be -infinity to infinity. Okay. And the radius of convergence, which is another concept with which we should be familiar. Okay. And again, don't get too spooked by this. We'll call this, again, this is r. R is equal to the radius of convergence here. Okay. What is a radius, in general terms here? What are we finding when we find the radius of something? It's a distance from the center or midpoint, from the center to what? Like an edge, right, or an endpoint, right? So in a circle's case, right, the very basic sense, when you first learn the word radius, right, in a circle, it's the distance from the center to the edge of the circle, okay? So for our purposes here, the radius of convergence, okay, is going to be the distance from the center of our, power series, okay, to the end or edge of our convergence. But where does our convergence end? It's infinite, right? So r will be an infinite length in this direction. Oops. There you go. And an infinite length in this direction. Right? And so there's where you get that r equal infinity there. Okay? Is a distance from the center, and it's just going infinitely in both directions from the center there. Series converges for all x, r equals infinity. All right. Where we will be spending most of our time is in this B, okay, this B section. The series will converge for only a finite window. Absolute value of x minus c less than r, with c being the center of this window and r, again, being that radius of convergence. Okay? So again, you can think of r as being the plus or minus value away from the center. Right? Just like we talked about here, the distance from the center. Okay. For example, here, right? Back in our geometric series, all right. What's the center of this geometric interval of convergence here? Zero, right? Centered at 0. And what is the radius of convergence here? Yeah, the distance from the center 0 to either the positive direction or negative direction there. It's 1 in either direction there. So this radius of convergence here would be 1. Okay. Interval converges negative 1 to 1 kind of thing. So same idea here, just more in general terms. Okay, so again, C being the center of the window, R being the radius of convergence. So this interval of convergence can include 1, none, or both endpoints. So in other words, not only will we be coming up with the interval like we talked about up here, right? We also have to be checking those endpoints to determine whether they, work, quote unquote, or not. All right. So what does that look like? Well, it's going to look something like this. Okay. So again, we'll be centered at some C. Okay, and then for that radius of convergence, okay, we'll go out some value, some r there, and then what will be the new coordinate here? We're at C, we go out r from it, what will that new coordinate be? Or how can we represent the new coordinate? C plus r, right? C plus r out. But of course, a radius doesn't have to go in the positive direction. It can also go in the negative direction. So I'll try and draw that roughly the same distance there. Not bad. Okay. And then, again, go r from the center in the opposite direction. What will the new coordinate for this point be then? C minus r, right? C minus r. Okay. Exactly. Okay. And again, this is just kind of like this idea of this radius converge there. So, and now we have kind of like a not infinite, I guess. I mean, but anyway, it's this interval now. I get a different kind of interval there, right? It doesn't go on forever. There are some x values that will work, some x values that will not work to make it converge. All right, and then lastly, this one's not very interesting, I guess. The series converges at one point, namely C. Okay, namely C, and that would look something just like this. Okay, and the radius is 0. So you have no interval here. It just converges at a very specific point, only at the center C. Okay, only at the center C there. Okay. So those are our kind of big concepts here. Like I said, we're going to be spending most of our time today, I think, in letter B there. We're in a C. Let's check here. Pretty much all in letter B. Yeah. Okay. Looking at these kind of finite windows, I guess I'll say. All right. So let's move on to see an actual problem here, right? All right, so we've got some power series here. These do not necessarily match up to any of our power series functions that you have to have memorized, right? Some of these are just kind of random problems that are just made up, right? We have those 4 basic ones you need to have down, all right, in preparation for the quiz tomorrow, right? E to the x, sine x, cosine x, and 1 over 1 minus x. But these are some other power series whose convergence we can also determine, okay? So in fact, looking at letter A, is this one of our familiar power series? It's close, but it's missing something. What's it missing? The factorial, right? Otherwise, it would be what? Otherwise, it would be e to the x, right? So this is, not e to the x, sadly. No factorial. Okay, so not e to the x, no factorial. In fact, I'll just go ahead and zoom in on just letter A there. We need to see letter B as well. Okay, so we've got 3 things we've got to find here. A center, the radius of convergence, and the interval of convergence as well. Okay? So, knowing what we know about power series, we can actually identify the center right away. What is the center going to be here? Right, our C is 0, right? Our C is 0 because, again, it's x, not plus or minus any other number except for 0 there. So exactly, the center here, well, it's just going to be C equals 0. Since x to the n equals x minus 0 to the n. Okay? So we just see there that x is not being shifted left or right at all, right? There's no number adding or subtracting to it. So we just have that shifted 0. So that's easy to identify. Okay, c equals 0, bless you. Okay? Yeah. And so we're going to have to use a test here to determine this convergence. And we're going to be focusing mostly on geometric and ratio tests. Oops, I'm off the screen. There we go. So we're going to be using geometric and ratio tests here. Okay. In this specific case, can we use a geometric test to show convergence here? Yeah, no. What's the thing that's throwing us off with that? The n, right? The n, the divide by n piece, right? Geometric is only for something to the n. If this n were being raised to the n power, then we can maybe get away with it. Potentially there. But anyway, right now this is definitely not geometric. It's a ratio test. Okay. So limit as n approaches infinity, right? Remember this, of the absolute value. Okay, and we put them in a ratio. I'm going to do the it's the first term, right? Over the next term divided by the previous term, right? So the next term here, that would be represented as what? X to the what? N plus 1 over n plus 1 times, and again, I'm not going to divide, I'm going to just multiply by the reciprocal, so times, and then what would be the previous term here? Or the reciprocal of the previous term? Yeah, n over x to the n, very good. Okay, and of course for the ratio test, we're looking for the interval of convergence, so we want this quantity to be what? What's that? Well, for a ratio test, we want to be less than 1, less than 1. Yeah. Ratio test, for ratio test there. Yep, less than 1. Okay. Remember, ratio test is like a geometric test in a sense. Okay. So let's simplify this sum, right? We can simplify this. All right. X to the n plus 1, dividing that by x to the n leaves us with what? Yeah, we can just subtract, right? When you have division, you can, in the same base, you can subtract the exponents. So the n's will subtract, we'll have just x in the numerator times the n over the n plus 1, right? We can't really simplify that too easily there. All right. If we do a direct substitution of infinity in here, we're going to get infinity over infinity, right, which is indeterminate. So we'll apply L'Hopital's here. I'm only going to show this just for this problem just because I don't want to have to write it out over and over again kind of thing. Okay. With an application of L'Hopital's, by the way, we're going to take the derivative with respect to what variable when we apply L'Hopital's here? It's, n. N is that variable there. So the derivative of n is just going to be 1. We'll have x over, and then x over, and then the derivative of n plus 1 will also just be a 1 there. So it's really just x, right? I guess I can kind of like well, yeah, the ends kind of disappear. So anyway, I'm going to go this way. So I'm here. Okay, so in other words, we get just the absolute value of x is less than 1. Okay. Or in other words, -1 less than x less than 1. Okay. So there's our interval of convergence. Well, kind of there. We're getting there. We have to check our endpoints still, but at least there's the basic interval. Okay. Can you see the center based off the interval here? What's halfway between -1 and 1? 0 is, right? And did we just establish earlier that the center was going to be c equals 0? So you can see the center right there, right? If I just kind of like imagine cutting that in half, we get c equals 0. Okay. What is the radius of convergence here? 1. Yeah, 1. Yeah, radius of convergence is 1. Okay. And then I saw, Carrie, you had a question?
Yeah, so like the first time that we figured out that the sine was 0,
Mm-hmm.
like how do you do that? Because you said that like x to the n equals x minus 0 to the n, like
Yep.
it's confused on that.
All right. Yep, I got you. I'll get you. Okay. So if we, so going back to here, okay? So remember, power series, the kind of like generic formula or generic form for a power series is this, right? It's called, that is called a power series centered at C, right? And so if we go to here, you can see then, where does the C, where does that center C show up? It shows up here with the x being raised to that n power. So you go back to what we had originally here, where you see the x being raised to the n power. Only option for c there is 0, right? C's got to be 0. Okay? Okay. So, I mean, if you want to quickly also see, I mean, if you just want to take a quick look, letter B, right? Where are we going to be centered at there? Anybody? Center is 0 there, right? For letter C, our center will be -3, right? Very good, because it's x minus c, so c would be -3. And for letter D, what's our center going to be there?
4.
Yeah, it's going to be 4. Yeah, it's the only thing that's only x there, and an x minus 4, so +4 will be our center there, okay? So those you can quickly see. So does that make more sense now, Carrie? You got that?
Yeah.
Good. Okay, so moving on here. Now, we've got kind of our interval here, but we've got to check those endpoints, right? Because the endpoints, both may work, one may work, neither may work. All right, and in fact, if we look, okay, so if we look, and I'm going to kind of bleed out here a little bit with where I'm writing, but we'll just make it work. All right, so, but what about x equals 1 and x equals -1? Okay, but what about x equals 1 and x equals -1? The endpoints, right? What about those? Okay. Well, remember, what do we know about the ratio test? If it's equal to 1, right, it's inconclusive here, right? I think we're inconclusive. The ratio test doesn't help us there. Okay? And so we are inconclusive. Okay? Because if you imagine plugging in, I mean, I'll kind of show the work up here. If we go back to kind of like our original, let's see if I can, there we go. If we go back to our original kind of ratio here and imagine plugging in 1 or -1 in for, and I'll plug it into this piece right here. Imagine plugging 1 or -1 here in for x. Okay, you're going to have ±1 in for x times n over n plus 1. All right, and that is equal to 1, which remember from the ratio test, that's inconclusive, right? Okay, so the endpoints, plugging them back into that test, testing them ourselves, right, checking them, we see that we end up with this inconclusive kind of idea. What can we say? All right, so I'll write that here. At x equals ±1, we are inconclusive by ratio test. Ugh, ran out of space. We are inconclusive by the ratio test. Okay, so the ratio test fails us here, right? Helped us to figure out the interval of convergence, but fails us with the determining, looking at the endpoints. So, well, maybe we can do better here. So over in this little space I'm going to create, here. We'll test the endpoints. Okay. Let's go back to our original series here. And let's test x equals 1. Okay. If x is equal to 1, our original series will now be the sum from n equals 1 to infinity of what? So x is 1, right? So the x that our original series had there, it's going to be replaced with a 1. 1 to the n over n factorial. I wrote a factorial, but it's not supposed to be a factorial. Sorry. But thanks for pointing that out. Okay? 1 to the n over n is what it's supposed to be. There you go. Okay? But what does this simplify to be? What is it really? 1 to the n is really always going to be what? 1. And 1 over n, the sum from n equals 1 to infinity of 1 over n, that is a what kind of series? P series. And in fact, is it a convergent or divergent P series?
Divergent.
Well, so P is equal to 1, and it is a divergent P series.
What did I say?
Yeah, you did say it. You did say it. Okay. P series diverges. So, are we going to include x equals 1 in our interval of convergence? If x equals 1 leads to a divergent P series, then we are not going to include 1 in our interval of convergence, right? So x is not equal to 1 there. Squeeze that in. All right, let's also test x equals negative 1. All right. So now if I test x equals negative 1, we're going to have the sum from n equals 1 to infinity of negative 1 to the n over n, no factorial. Okay, yes, right? Can we use P series here? No, because it's now alternating, but as Mario said, this is an alternating series now. Okay, we have to remember back to alternating series, right? We have to check to make sure that the limit as n approaches infinity goes to 0. It does, check. We also check to make sure that the next term, again without the alternating piece, in both cases, without the alternating piece, will the next term be less than the previous term? Yeah, 1 over n plus 1 is going to be less than 1 over n, and so this converges by alternating series. I don't have the space to do all that work out there, so we just did it, verbally. So, do we include x equals negative 1 in our interval of convergence? Yes. So, x equals negative 1. Okay? Phew. So, going back then to this original interval of convergence, we have to make a few corrections, right? Or one correction, I guess. We'll say negative 1, and then what should this inequality symbol be here? Less than or equal to, because we do want to include the negative 1, and then what should this next inequality symbol be? Less than, no equal to, because we don't want to include the 1. And so there is our interval of convergence. Okay. So we can determine this power series will converge for any x values between and including negative 1, excluding 1. Okay? So there's the idea. So interval of convergence, center, and radius of convergence. Okay, that was a lot. Okay.
Is this every single problem?
Like I said, some of the problems won't be that second case. Let's take a look at letter B. Any questions on that before we move on? I know that was a lot. Okay, but again, we're also just learning it, so I wanted to take my time a little bit more there with that one. So we're good though? Easy peasy. Great thing to come back to from spring break. Just what you wanted to do, some really intense mathematics. All right, center is, what we say for letter B here? c equals 0, right? Okay, we can all identify that, right? There's no number with the x that we're subtracting or adding, right? So it's just centered at 0. There's no c there, so c is 0. All right, let's again do our ratio test here with this. See if that ratio test works. It's definitely not geometric, right, because we have that n factorial hanging out. Let's do our ratio test. So it's going to be n plus 1. I put an x when I said the word n there. N plus 1 factorial over x to the, what am I writing here? Yeah, sorry, let me redo this. Okay, sorry about that. Yeah, so n factorial, and this one you can go ahead and just write as the fraction. X to the n plus 1. Ah, my gosh. I just made a joke about doing really intense mathematics and it being fun, and here I am, brain stopping from work. There we go. Okay. I did it while talking too, which is an amazing feat for me to do two things at once there, right? So there we go. All right. Second term divided by, or next term divided by the previous term. Okay, got it. Spit it out there finally. And then we want that again to be less than 1. Less than 1. Man, I really messed this up in my notes here. That's what the problem is. There we go. Okay, so what can we simplify here, or what can we cancel out, or what does it simplify to be? Yeah, so the factorials here. N plus 1 factorial over n factorial. What does that simplify to be? Just good, n plus 1. Yeah, okay. I know some people were still having trouble with simplifying the n factorials n plus 1. If you need to, expand it out, right? So you could write out like, n plus 1 times n minus 1, dot, 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 kind of thing. And then here for n factorial, that'll be n times n minus 1 times n minus 2. And you can see, oh yeah, the n's, the n minus 1s, and everything else cancels. You're left with just the n plus 1 in the numerator. And then what about the x to the n plus 1 over x to the n? That will simplify to be what? X. Okay, and that's all over 1, I guess I'll say there. I didn't have to write that, but I did it that way. Okay, so now we plug in infinity, right? Or like imagine direct substituting here, and we get infinity times x. Okay, is that an indeterminate form? Can we apply L'Hopital's here? No. Yeah, no. So infinity times x is really, right, infinity less than 1, and that is, yeah, never true. Never true. So our interval of convergence then would be what? Yeah, the radius is 0, right? There is no interval of convergence. It never converges, okay? So the radius would be equal to 0. Okay, radius convergence would be equal to 0. Okay, and x equals 0 is the center, and there is no interval of convergence there. So there you go, Mario. That was a nice... If I hadn't messed up the beginning, at least, it would have been nice and easy. Yeah. Okay. Easy peasy. So there's your first, or your third case, I guess we said. Third case there. Okay. Feels good, man. Okay. Questions on letter B? Oh yeah, Sean.
Why can you not use L'Hopital's?
Not indeterminate form, right? It's got to be like infinity over infinity. Just x times infinity, or infinity, right? Not indeterminate. We see that is exactly what it is. It is infinite, right? Goes on forever. Never less than 1. So, okay. All right. I'm going to do some very creative dividing here. There we go. Perfect. Some more creative dividing over here. Perfect. Okay. So a little puzzle piece. All right. So let's take a look at letter C. All right, so why don't you guys go ahead and No, I'll set it up for you. I'll set it up for you. All right, so first of all, what's the center here?
I wasn't ready.
Yeah. Okay, center is -3. He wasn't ready. Okay. Yes, the energy in the room became very negative suddenly, and I was like, uh-oh. We'll at least get you set up here. Going to lose them. All right, so we're going to use ratio test again, right? Have to use another ratio test. It's not geometric. We got that alternating piece in there. We've got n minus 2, to the third in there as well in the denominator, so it's just not going to work out. So let's write this out. Now, the alternating piece, is that going to be necessary for us to include in our ratio test here? Why not? All right, it's inside of absolute values here, so we're going to just drop that alternating piece. Doesn't matter positive or negative here. We're just going to drop the alternating piece altogether. It's not going to be necessary for our purposes. And so again, I'll do the next term. So that'll be x plus 3 to the n plus 1 power over. And then n minus 2 to the third, what does that become as the next one? N minus 1, right? You just imagine replacing that n with an n plus 1, but that'll be minus 2. So it just becomes n minus 1 to the third. Okay? And then times the reciprocal of the previous term there, right? Because we're dividing, really. So n minus 2 to the third over x plus 3 to the n. And again, less than 1.
Hold on, how do you get the center?
The center. So if you look here, right, now the x has plus 3 there. So what is that plus 3 going to do? Right, think about your transformations, like way, way back when we talk about like transformations and things like that. When you add a number or subtract a number from x, that's a horizontal shift. So we're taking our normal center at 0, right? That x plus 3 is a horizontal shift to the left. Sorry, because of the plus 3. It's only the value with the x. So you look back up here, right, at letter A, there's no number with x, so 0 is our center. At letter B, there's no number in with x, no shift, center at 0. If you look at D, right, x minus 4. So that's a shift right 4. So C equals 4. Exactly. Okay? Just a transformation there. Right. So back to this. Let's simplify it some. So you'll still have the x plus 3 in the numerator there. 1 x plus 3 to the 1. Okay? And then n minus 2 cubed over n minus 1 cubed. Well, I'm going to kind of group those together. Okay, thusly. And I'm going to kind of skip the L'Hopital stuff here, just in the interest of time, kind of moving on. But if you really, if you're doing this in a free response question, you'd want to show that it's indeterminate form and then apply L'Hopital's. Now, of course, in this one, it's kind of yucky. You have to apply L'Hopital several times in order to get down to what we want. Okay. What we know this is going to go to, though, just by it'll be so it'll be a 1 right here, right? Because we have a lead coefficient of 1, both have degree of 3, and so as n approaches infinity, this is going to go just to 1, and so then the overall thing inside the absolute values will just be what? Absolute value what? X plus 3, okay? And that must be less than 1. Okay, so this goes to 1. Okay, so it'll be 1 times the quantity x plus 3 there. Which then, for our interval then, that's going to become -1 less than x plus 3 less than 1. And then to finish solving for x, we should do what? Subtract 3. So -1 take away 3, -4. 1 take away 3, -2. Be careful when you subtract 3 on both sides there, right? -1 take away 3, that goes more negative to -4. And then 1 take away 3, again, -2. Okay, so do be careful with that. If you remember, we did problems kind of like this in a previous section that we covered, right? Where you were asked to determine, like, for what value of x would these, these certain series converge. If you remember, I think it was like last unit that we did that. They would come towards like the end kind of thing. I think it showed up as a question as well in your free response and stuff. I think I can say that now because, oh no, we still have some people that have free response to take. So never mind, that didn't happen. All right, so we'll just keep moving on here anyway. Not that anyone pays attention to me 100% anytime, so most likely everyone, you probably missed it if you weren't listening. So anyway, all right, so can we see our center here at -3? There's our interval. Is -3 in the center between -4 and -2? Yes, it is, okay. And so I'm going to, again, kind of just like indicate that there. C equals -3, halfway between. What is our radius of convergence going to be here then? 1, right? Yeah, we are 1. Radius equals 1. Oops. Okay, radius is 1. And so now we have to test our endpoints. Now we get to test our endpoints. So we'll try. So test here. We'll test x equals -4 first and see if that one works. Okay. So plugging -4 in for x, we will get, well, so we do need to still keep that alternating piece there, the negative 1 to the n plus 1, times, and then let's see here. Whoops, I shouldn't have done that many. Oh well. X plus 3, but if I plug the negative 4 in for x, okay, so now the negative 4 goes in for x, right? What's negative 4 plus 3? Negative 1 to the n over, and then, well, now n minus 2 to the third still. So it is an x value we're testing here. So that do not plug that negative 4 in for n, right? It's an x value. X is negative 4. We're testing the interval of convergence here. It's an x value. So only plug it in for x. Okay. Well, we can do a little bit of simplifying here, can't we? The negative 1s. They can go together. Yeah, and if it's negative 1 to the n plus 1 times negative 1 to the n, that'll become negative 1 to the 2n plus 1. Negative 1 to the 2n plus 1 over n minus 2 to the third. And now it's up to us to determine a test to use to check this out. So we should probably use the alternating series test here, right? This thing is alternating, right?
No, it's not.
It is not alternating. Mr. Witt, there's a negative 1 raised to a power, though. But what is this power always going to be?
Odd.
Always will be odd. Therefore, this will always be a negative value. Okay, so it doesn't. We don't have to use alternating series test here. Bless you.
Thank you.
Okay, so we can actually take this. This is always going to be negative 1. So we can just go ahead and just take that negative 1 out, and say, okay, it's going to be negative 1 times the sum from n equals 3 to infinity of 1 over n minus 2 to the third. Okay, this negative 1 to the 2n plus 1 will always be a negative 1. So you can just pull the negative 1 out and then just get this right here. Now, 1 over n minus 2 to the third, we can't, there is no test for 1 over n minus 2 to the third, but we can compare it to what? A p series 1 over n cubed. So versus 1 over n cubed. What do we know about 1 over n cubed? That is a p series that converges there. Okay, so 1 over n cubed converges. This will converge, okay? And so therefore we know that negative 4 works. It's in our interval of convergence there. Okay, so interval of convergence. There you go. All right, and we'll include the negative 4, and then now we're going to see if we'll include the negative. Oh, yes, question.
I'm just confused where we got the n equals 3.
And to the third, you mean?
Yeah, that.
Right there?
No, on the, like, way back in the beginning, like, not in the beginning, like, when we started
Your
testing
end
it.
value changed.
My n value changed?
No.
Oh!
N equals 3.
It's supposed to.
Because that's where it started with the original problem.
Oh,
So that's all. Yep. Kara?
Are we able to pull negative
Oh, wait. Let me pause real quick here. And the reason why we have to start with n equals 3 there is because then we'd be undefined, Caitlin. If we started at 1 or 2, we'd be undefined because we eventually get to 2 and be divided by 0. So yes, sorry.
Like, how were we able to pull the negative 1 out, and then what happened to the 2 and
So, okay. So we were able to pull that negative 1 kind of like out because negative 1 to the 2n plus 1, it'll always be a negative 1, right? So all the terms are going to be, negative 1 over something plus negative or minus 1 over something minus 1 over something. And so it's like essentially it's just we can like kind of like imagine factoring out that negative 1 from all those terms. So you can pull that negative 1 in front. It's just like undistributing the negative 1 to all the terms there. Does that make sense? Yeah. So, and that's a property of all of our series, right? If you have 3 over something, you can pull that 3 out front as well, kind of thing. Okay, if it's just a plain old 3. All right. Whew. One more here. All right. Let's try x equals negative 2 now. All right. So sum from n equals 3 to infinity, negative 1 to the n plus 1 times, and then now if I plug negative 2 in for x, we're going to have we're going to have positive 1 to the n over x n minus 2 to the third. Okay. So negative 1 to the n plus 1, that's the alternating piece. Plug in negative 2 for x, you get positive 1 to the n over n minus 2 to the third. Okay. Does this series alternate? Yes, because 1 to the n is just going to always be 1, and so this is really the sum from n equals 3 to infinity of negative 1 to the n plus 1 over n minus 2 quantity to the third. So this is alternating series, so we can use the alternating series test. Is it going to converge or diverge by the alternating series test? Well, let's check. Step 1. The limit as n approaches infinity of 1 over n minus 2 to the third. Okay. What does that limit equal? 0. So check. That's right. And then we also got to check the next term. So the next term will be 1 over, let's see here, so it's going to be, the next term will be plus 1, so it'll be n minus 1 to the third, and that's going to be less than 1 over n minus 2 to the third, like that. Okay. Did I? Let me see, make sure I set that up right. N minus 1, right? Its next term must be less than the previous term. Okay, so, I mean, think about it this way. You can just, like, let's just pick a value here. Let's just say, like, 10. So 10 minus 1 will be 9 to the third. 1 over 9 to the third. Is that going to be smaller than 1 over 10 minus 2, 8 to the third, right? And so 9 to the third is going to be a bigger value, but then 1 over that will be smaller there. So this is true too. This holds true, right? And so it converges at x equals negative 2. And so then that means our interval convergence is negative 4 to negative 2, including the endpoints there. Okay, including those endpoints.
Do we have to do it like that, or can we just leave it in the...
You can leave it inequalities too. That's fine. Yeah, inequalities too. I just did a different way there.
That's too much work for me.
It is a lot. It is a lot. It is a lot. I agree. All right, let's keep it going here. Keep it rolling because we got to keep moving here. All right, I'd like to get through the next page too. So just the front on the next page there. So we can do this, I think. All right, so we already established the center here is 4. Okay, center is 4. So again, we'll do our ratio test here. Again, this negative 1 to the n piece, I'm going to drop it, right? Not important for our purposes here because we're doing absolute value, so it's just going to get eliminated, negative 1 to the n, the alternating piece there. All right, so instead we'll just focus on, so it's the next term, so it'll be n plus 3, okay, times x minus 4 to the n plus 1 over n plus 1 times 3 to the n plus 1, and then times the reciprocal of the original, so it's going to be n times 3 to the n over n plus 2 times x minus 4 to the n. I want that again to be less than 1. Okay. So far, so good on that step. All right, so again, simplifying things out, let's see here. The 3 to the n in the numerator and the 3 to the n plus 1 in the denominator, that will cancel out and leave us with a 3 in the denominator, right? 3 to the n and 3 to the n will cancel, leave us with just 3 in the denominator. Let's see here. And then nothing else really cancels. Oh, yes, the x minus 4 to the n plus 1 and the x minus 4 to the n. Okay, so we'll have x minus 4 to the n up there. So we'll have something like this. Okay, what I'm going to do is I'm going to bring my x to, again, my x kind of parts out front there. So we'll have just x minus 4 over that 3. Okay, and then I'll group all my n terms together. So anything without an n, I'll group together and then multiply with anything with an n. So then we'll have n times n plus 3 over, looks like n plus 1 times n plus 2, right? Okay, and I group these together specifically on purpose because we're taking the limit as n approaches infinity here. And when I group those together, we can see that, well, what will this groupings of n approach? It's going to go to 1, right? The degree of the top is n squared. The degree of the bottom is going to be n squared. Their lead coefficients will be 1. And so, yep, it's going to go to 1. Again, not applying L'Hopital's there or anything, just kind of jumping the gun. So we end up then with x minus 4 quantity over 3 less than 1. Okay, which then becomes negative 1 less than x minus 4 over 3 less than 1. And so we get negative 3 less than x minus 4 less than 3. Again, multiplying both sides by 3 there. And then adding 4 to both sides. 1 less than x less than 7. So, do we see our center here? Is 4 in the middle of 1 and 7? Sure. Well, again, midpoint formula, 1 plus 7, 8. 8 divided by 2, 4. So there's our center, 4. Okay? What's our radius of convergence here? Yeah, radius of convergence is 3. Okay, so there's our center and our radius. Okay, and then we'll test our endpoints here. Okay, so let's try x equals 7, which will result in the sum from 1 to infinity of negative 1 to the n plus 2 over n times 3 to the n times, and then 7 minus 4 is 3 to the n. Well, that worked out nicely. When we plug in the 7 there, we end up with 3 to the n, right? 7 minus 4 is 3 to the n. What's going to happen here? What can we simplify? Yay, cancel those 3 to the n's. Okay. And so then this simplifies to be the sum from n equals 1 to infinity of negative 1 to the n times n plus 2 over n. Okay? What is true about this series? It will... It's alternating, that's true, but we don't need the alternating series test here, because alternating series test shows convergence and this thing diverges. Okay? Use the nth term test for divergence here, right? The limit of this thing as n approaches infinity, it's going to be, well, plus or minus 1, right? It's going to be positive or negative 1, which is not 0, right? Not 0. Okay? The limit as n approaches infinity of n plus 2 over n equals 1, which is not equal to 0, so it diverges. Oof, gotta keep moving here. X equals 1. Well, again, so let's see, negative 1 to the n plus 2 over n times 3 to the n, and then 1 minus 4 is negative 3 to the n. Okay. Can we cancel anything out here? Right, so we can combine together here, for example, the negative 1 to the n and the negative 3 to the n, right? They're the same exponents. We can combine them together. Negative 1 times negative 3 will become what? 3 to the n, and there's a 3 to the n in the denominator. So this, and this all cancel. But what do we know about this series? N plus 2 over n, what's it going to do? Diverges. So our interval of convergence then will be 1, 7, excluding both. Okay, 1, 7, excluding both endpoints there. Questions on any of that? Okay. Give this one a try. Number 2, go ahead. Give you a few minutes here to give that one a try. Okay. Maclaurin series, sine of x, right? That should be something we're familiar with. Remember, sine of x is even or odd? Odd, okay. Sine at 0 is 0, so your first term is 0, and then you want to go all your odd powers and factorials after that, okay? So if you want to write out the first 4 non-zero terms, and then determine the interval of convergence for this function. Okay.
How do you remember that it's odd?
So you know what the picture of sine looks like? The graph of sine looks like this.
Yeah.
So an odd function, if we were way back in like algebra 2, maybe algebra 1, odd functions have rotational symmetry. If you rotate this 180 degrees, it'll match up to itself.
Okay.
So it's an odd function.
Okay.
Okay. Whereas cosine looks like this. Symmetric about the y-axis. That's an even function. Even functions have symmetry about the y-axis.
Okay.
Right? You think about the function x squared, right? Symmetric about the y-axis. The function x cubed, rotational symmetry, and those are odd and even degrees. That kind of deal. Okay, that can help you with that.
I feel like I'll remember it by maybe like opposite of or adjacent sine is odd.
Yeah, you can think of it that way. Yeah, that helps too. Yeah, do it that way. Yeah, whatever you need to help you remember it. Whatever makes sense to you. So I went ahead and wrote out your first 4 non-zero terms there, okay, as well as like the the general term, as well as the series, okay, for it. Then you guys now need to evaluate the interval of convergence there. Remember, that's a ratio test. Remember, when you plug in that, when you find that next term, n plus n gets replaced by n plus 1. So that 2 will distribute, kind of thing. 2n distributes to, 2n plus 2, 2n plus 1. Okay, so there I have your setup too, if you want to check your setup.
Wait, why are you going like 2 terms forward?
Because there's a 2 in front of the n. So when you replace, when you find the next term, you plug n plus 1, you replace n plus 1 with n.
Okay.
N with n plus 1, and so that 2 distributes.
Alright.
Which makes sense because in sine we're kind of skipping every other term, kind of thing. So it makes sense we have to go, kind of 2 more instead of just 1. Or maybe it makes sense. There's your simplification of your ratio test. Okay. The factorial there, 2n plus 1 factorial over 2n plus 3 factorial leaves 2n plus 3 and 2n plus 2 in the denominator. I forgot my parentheses. Okay. Yeah, right. So what is the limit of this quantity here as n approaches infinity? It goes to what? 0. And so we're going to have x squared times 0. And what's x squared times 0? 0. And when is 0 less than 1? Always. Always. So what's our interval of convergence here? Negative infinity to infinity. Okay. Question.
Why is it 2n plus 3?
So when you plug that n, when you find your next term here, okay, plug that n plus 1. Imagine putting in, I think I'll just do it here.
Oh, yeah, I got it.
You got it, okay? Ariana, question?
Wait, who's doing
Since we're putting the absolute values, right, it doesn't matter whether it's going to be positive or negative, the absolute values will take care of it either way. So we can just kind of forget about it when we're doing the ratio test.
Can you work out how it got
Yes.
to 2n plus
Yep, absolutely. So the next term here, right, it's going to replace the n. So you have like 2n plus 1, right, factorial. The next term will be 2n plus 1 factorial like that. So the 2 has to distribute. The n gets replaced. It's like you're plugging in n plus 1 in place of the n there. So that's the 2 distributes. Okay, which gives you then 2n plus, well, 3 factorial there. Okay? All right. Last one. I think we can do it. We'll see. Well, so basically just a summary here, right? Interval of convergence. So this shouldn't surprise us, hopefully, right? Because we already know that this series is precisely sine of x, right? This series, as we go to infinity there, converges is sine of x. So it makes sense then that the radius of convergence is all real numbers because it is exactly sine of x for any value there of x, okay? Any value, all right? So you could do the same thing to our e to the x. You could do the same thing to our cosine of x. You could do the same thing to the, well, not the 1 over 1 minus x because that's a geometric series, but at least those earlier three, right? Those would converge there, okay? For all of them. All right, so number 3, last one here. The Taylor series for the function f of x equals ln x is this, okay? Find the interval of convergence for this function, okay? And then find the value of the sum from 1 to infinity of negative 1 to the n minus 1 all over n. All right, so let's get this last piece done here. Okay, again, I'm going to drop the alternating piece, not important for our purposes. We'll have x minus 1 to the n plus 1 over n plus 1 times, and then the reciprocal there, so n over x minus 1 to the n. And we want to see if that's, when that's going to be less than 1. Okay. Manipulating some things around here, right? We'll have an x minus 1 in the numerator times, and then we'll have n over n plus 1. N over n plus 1 as n approaches infinity is going to go to what?
1.
Goes to 1. And so we end up with then x minus 1, absolute value of x minus 1 less than 1. So negative 1 less than x minus 1 less than 1. And so we get 0 less than x less than 2. Okay? We didn't identify this earlier, and we don't need to in this one, but what is our center here? 1. What is our radius of convergence here? If the center is 1. Yeah, the radius is 1. Okay, that's not actually, you weren't asked that, so I'm not going to bother writing any more of that down. So we just got to check our endpoints here. Let's check x equals 0. Okay, so we plug in 0 for x, and we'll end up with the sum from n equals 1 to infinity of negative 1 to the n minus 1, and then negative 1. Nope, it's, what am I doing here? Yeah, plug in 0, so it's going to be negative 1. When you plug in 0 there for the x, it'll be negative 1 to the n over, and then just n. Okay, combine these pieces together here. Negative 1 to the n minus 1 times negative 1 to the n will become negative 1 to the what? 2n minus 1 all over n. Okay? So alternating series test, right? No, because that negative 1 to the 2n minus 1, does that alternate? No, it's always odd. It's always odd, again. And so we can't do, we can't use alternating series test here. And so again, it's always going to be a negative 1. You can pull that negative 1 out. You're going to have 1 over n. What do you know about 1 over n? It diverges because it's a divergent p series. P equals 1. Okay, so not alternating. Okay, diverges. P series. P equals 1. All right, x equals 2. Sum from n equals 1 to infinity. Negative 1 to the n minus 1. 1 to the n over n. Okay, so now we plug in 2. 2 minus 1 gives us 1 to the n there. Okay, what do we know about 1 to the n? It's always what? 1. And so we end up with just negative 1 to the n minus 1 over n. Is this alternating? Yes. Will it converge? Yes. The limit as n approaches infinity of 1 over n will be 0, so that's checked. The second term, or the next term, n plus 1 over n plus 1 will be less than 1 over n. Check, that works, so it's alternating and converges by that test. And so our interval is 0 to 2. Okay. And so what we know then is that this sum that we just determined converges from between 0 and 2. It is exactly equal to the natural log of x for all x's from 0 not included to 2 included. Okay? Now, look at what we have up there, the thing we're supposed to evaluate. Sorry here. Okay, just almost done. All right. This, well, I'll just finish up tomorrow. How about that? All right. So we'll stop there. Okay. I'll finish up. So close though. So close. Yeah.
Is there anywhere where like converges conditionally or where does the condition like start to matter?
So that will. It doesn't. It won't. I don't think it matters right now. Like we're just worried about convergence. That's it. Conditional, unconditional, not a big deal. Set requests for today. Set requests. Yes. Because we do have that quiz tomorrow too. So thank you, Karen. Yes.
It's not what we just learned, right?
Other set requests. Michael.
It's not on what we just learned, right?
Correct. Yes. Tomorrow's quiz will not cover what we learned today. Tomorrow's quiz will not cover what we learned today. Okay.
I'm taking my test prep today,
Yes.
and I can't go to school for the last 2 parts.
Yeah. It should be fine.
Okay, I have track practice that I have to go to, but I think I should be able to get it done.
Okay.
Also, on the review quiz for tomorrow's,
Yes.
on the FRQ part B,
Yes.
I understand like how everything happened. Here you can look at it. Except they multiplied by 2 in the final answer, and like I'm confused on how that 2x impacts it. Does that make sense?
Oh, I see what you're saying. Yes.
Because like I understood how to make it so like if it's an integral, then like for the first one, that's like f prime. It's just gonna be f, like that kind of thing. I just don't
Right.
get how the 2x plays into it.
So the 2x because so you have to integrate, right? You replace the 2x. So all the time, I think very well. And all those 2's, you're going to kind of like take. You're just gonna all those 2's that you plug in. You can like imagine like backing those 2's out, I guess, kind of thing. And so that's going to then create then that 2 times the final answer.
Okay, that makes
Kind of
sense.
deal. Does that make sense?
Yeah, I was just confused. And, like I understood you multiplied by 2. I just
Yeah.
don't know why.
Each one of those terms is going to have a 2 in it, so you, like because of the 2x, so you factor the 2 out, do your stuff with just x, then multiply the 2 back through, kind of thing.
All right, cool.
Yep.
Thanks.
All right, well, what's up, Megan?
Should I take my quiz from Thursday instead today or after school?
It's a quiz, right?
Yeah.
I mean, how good are you feeling about it?